Hello, everyone. If you're just joining us, we're going to start our program in just about 2 minutes at noon. So stick around. We've got a lot of amazing stuff, and it's a historic day. The Perseverance rover is going to land on the surface of Mars. Very, very exciting. We've got a lot of cool programming about it. So stick around. Just about a minute and 30 seconds, maybe even less, we'll get started. Thanks for tuning in, everyone. We'll get started in about 30 seconds for this very exciting day as the Perseverance rover lands on Mars, the 5th rover to land on Mars. Very exciting. We've got a lot of cool, amazing scientists and amazing people who worked on the mission and worked on Mars stuff for many years to talk about it. So I have a very cool program coming up for you in about 15 seconds. All right, and it is now noon. It's time for us to begin. Thank you, everyone, for joining us for this historic and very exciting day. The Perseverance rover lands on Mars. We have a lot of amazing presenters and amazing presentations. As you're watching, if you have questions for any of our scientists, please put those in the chat, whether you're watching on Facebook or YouTube. We will be watching those and we'll direct your questions to the scientists so they can answer them throughout the program. We probably won't get to get every question, but we'd like to try. Now, without further ado, I'd like to introduce Dr. Steve Lee, who is a senior scientist at the Space Science Institute in Boulder, Colorado. And for many years, he was a space scientist here at the Denver Museum of Nature and Science, our resident Mars expert, instrumental in creating this Mars diorama you see behind me. He recently retired and we miss him a lot around here. So it's great to have you back for this landing, Dr. Lee.
Well, thank you, Mitch, and welcome to everybody. It seems like it was just yesterday when I first showed up at the museum way back when that we were about to do our first rover landings on Mars, the Spirit and Opportunity missions. And here we are almost 20 years later, and we're gathering for another Mars landing. So I think what I'd like to do is quit yakking here and actually give you some background about the mission we're about to see today, the Mars 2020 program. So just one moment and I will get my PowerPoint up. There we go. So those of you that pay attention to Mars, this rover, Perseverance, that we're going to be watching today, it looks a whole lot like the last rover mission to land, which was the Curiosity mission in 2012. And the basic spacecraft is very similar. They're sort of fraternal twins. But as we'll see, the instruments on board and the capabilities are dramatically different. And so this is the latest in a long legacy of Mars missions. We actually had our first successful flyby of Mars in the early 1960s, and we've been going for almost 50 years now. So it's really, every mission builds on what the last set of missions brought to us. And so this is just a graphic showing all of the Mars and the US and European missions that are currently in orbit, and then the history of surface missions starting in the early 2000s. And so underlying all of this is a huge library of information that we've gained from these past missions. And the one thing that we know very well at this point is that today Mars is a very, very dry and a very, very cold place. So essentially it's a frozen desert. But the flip side of that is all of these missions have shown us that there's good, strong evidence that at some point in the past, Mars had a lot of water on the surface, a lot of liquid water, and that's just something that the temperature is too low. The temperature is too low for water to exist on the surface as a liquid. And so we think, based again on the mission observations, that about 3.6 billion years ago, the climate of Mars started changing very dramatically. It started losing its atmosphere. It started losing the liquid water. And so what was once very similar to Earth after its birth then became a very, very different place. So what that leads us to for all of these missions that we've been engaged in over the last many decades is trying to come up with the answer to the very basic question of, did life ever exist on Mars? And when I talk about life, I'm not talking about little green men. I'm talking about maybe little green single-celled organisms. That's what we're going with this mission today, to really make a good stab at once and for all answering that question. So what should we even look for when we get to Mars? And the only example of biology we have is what we find on the Earth. And so on the left, here's the classic fossils, little fish, leaves, dinosaurs. But all of those fossilized organisms are only about 650 million years old at oldest. But what we do find in many places are the biosignatures of microbial life. And those actually date back to this magic number of about 3.6 billion years. And that's what we see on the right. And what that is what's called a stromatolite. And we actually see these being formed today. And it's in shallow waters where the water is sort of lapping up and down and getting these things wet and then dry. And what these are mats of single-celled organisms, algae, bacteria, and they form pond scum, for lack of a better word. And then in the course of the water coming and going, it brings in a little bit of sediment, mud, elements or minerals that precipitate out of the water, and they form very, very thin layers as the bacteria and the algae grow. And so a great place to look for these today is in Australia. And here's an example. Just drive across the road and you come up with 3.5 billion year old examples of these stromatolites. And when you cut them open, you see this very, very, very fine layering structure. And when you examine that in detail, you see chemical signatures for the single-celled organisms that caused these things. And that's a very characteristic trait of these fossilized pond scums. And so this is the type of thing that we might look for. We'll try to determine if organic molecules that once made up the organisms are preserved in these rocks. There's minerals that are formed only by bacteria and only by algae. And if we find those sorts of minerals, that's a good clue. But the easier thing is to look at the physical and the chemical signatures for biology in rocks. And this again is a cross-section of a stromatolite. And so where might we look for those on Mars? Well, on Earth, a great place are these shorelines that I showed you a few minutes ago, or river deltas, where you've got lots of sediment coming in that can bury the biology and preserve it for potentially billions of years. So let's let's think about where on Mars we might find conditions like this. So this is a global map of Mars, and it just shows where all of the successful missions to land on the surface have been located. And so the ones that are currently active, or the only one that's currently active, is the Curiosity mission. And Perseverance is going to come down in an area that's called Syrtis Major. It's one of these dark features on Mars that if you're an amateur astronomer with a decent telescope, this would be very familiar to you at some times of the year. It's a very, very distinct feature on Mars. And so Perseverance is headed to a location called Jezero Crater. And this is a topographic map of Jezero. The blue is low, the green and lighter colors are high. So the rim of the crater is right here where my cursor is. It's about a 45 kilometer, 30 miles-ish diameter crater. And this ellipse right here is the targeted landing site for the Perseverance rover in just about an hour and a half. So what's exciting about Jezero is there's good evidence that when Mars was in its warm, wet phase early on in its history, that there were streams of water flowing into the crater. So this is sort of a riverbed flowing into the crater, and the crater became a lake. It was filled with liquid water, and then it flowed out the other side. And this is a close-up view of where that stream entered the crater. So it sort of broke through the crater rim here, and when it hit the lake, the flow of the stream slows down. So whatever sediment it's got that's being carried downstream, it drops out and it forms a delta, just like we see in the Mississippi River or most rivers that flow either into lakes or oceans. And this is by far one of the best examples of a delta that we see on the surface of Mars. And so here's our targeted landing site. It's just about 4 by 5 miles in dimension. This is by far the most accurate landing that we will have ever attempted on Mars. So the expectation is they'll come down very near this delta and be on a safe landing site, and then be well within the capabilities of the rover to drive up and sample the delta formation, look for the lakeshore deposits, look into this stream bed, and just do a very thorough biochemistry treatment for this area. And I think Mike Wolff is going to be showing or talking a bit more about all the instruments on board the rover. But this is just sort of a teaser for that every instrument on board the spacecraft is really very finely designed to address this question of could there have been life in the past on this location of Mars. And excuse me, the one thing that Perseverance will not be shy about is taking pictures. It actually has 23 separate cameras on board. There's 7 of them are used for science. There's 9 of them are used for various engineering things like charting the course for the rover, looking at the spacecraft itself, things like that. And then there's 7 cameras on the system that will bring it down to the surface today. So we'll actually have views of the parachute deploying, views of the ground approaching, views of the rover descending from the descent stage, things like that. So there'll be lots of exciting images coming out of this. And so the main purpose of the Perseverance rover is to go out and collect samples and analyze them, determine if there are signatures in this area. And the one thing that's very unique is that this mission is just phase one of a multi-part mission that's likely to play out over the coming decade. And so when a good sample is decided upon, the rover drills a core sample. It's about the size of, well, it's hard to even remember pieces of chalk since we seldom use blackboards, but something like that, about 1/2 inch in diameter by 2.5, 3 inches long. And there are 43 separate sample canisters on board the spacecraft. And so these particularly good samples, they will put into one of these sample containers. They seal it up so that it's totally enclosed and not in contact with its environment. And then over time, when they get to a waypoint that's useful or easy to find, they'll drop off some of these sample canisters and leave them behind. And then in subsequent years, perhaps as early as 2026, we'll launch 2 separate spacecraft to Mars. So this is the Perseverance rover. It's collected the samples by then. And there'll be another lander that sets down somewhere in the vicinity of where Perseverance is. And it will have a little rover on board. The rover will go out and collect the sample canisters that Perseverance dropped, and then bring it back to this lander and put it in an ascent vehicle, a rocket, and that launches the sample container into Mars orbit. There'll be a separate mission or separate spacecraft orbiting Mars. It will rendezvous with the sample container, pick it up, and then launch itself back to the Earth. So as early as, say, 2031, 2032, if all goes according to plan, we will have these sample containers back on the Earth. And in addition to all the measurements that Perseverance was able to do, that will give us access to the finest laboratories on Earth, just like we have done with the lunar samples that the Apollo missions brought back. And that should give us much greater capabilities to know whether the answer to that question about life on Mars is yes or no, or we still don't know. So we'll wait for that. So today is the beginning of everything. The spacecraft launched last July. It's been coasting to Mars almost 300 million miles since launch. Today is when it finally starts fulfilling its promise, and it will be building on the shoulders of these giant missions that have gone before. And hopefully over the next decade or so, we're going to be seeing an enormous amount of information coming back from this spacecraft, and we'll be getting some of these long-standing questions about Mars answered. So I think at that point, I will stop and turn it over to our next panelist. You're going to hear a lot more about the spacecraft itself now. We have 2 engineers that are going to be joining us and telling us a lot about how the spacecraft actually gets down to the surface. So the next presenter is David Scholz. He's with Lockheed Martin here in Denver, and he was the principal engineer for what's called the Mars 2020 aeroshell. That's the capsule that protects the spacecraft, gets up to Mars, lets it enter the atmosphere, and deploys it down to the surface. And David, by background, is a mechanical engineer. So welcome, David, and thanks for joining us today.
Thank you, Steve. Very happy to be here. It's a very exciting day. We have just a short presentation for you here about Lockheed Martin's role in Mars 2020. As Steve said, I was the principal engineer for the aeroshell here at Lockheed Martin, which meant I was responsible for getting it designed and built and tested and then delivered to our customer at the launch site. Next slide. So wanted to start with just a quick introduction. Who is Lockheed Martin? What we do? We're a major security and aerospace company, mainly supporting the defense industry and the space industry. We're involved in we have four major lines of business that are listed there. Of course, we're heavily involved in space. We've been involved with missions to just about every planet in the solar system at this point, and we've also had the good fortune to be picked to return samples from the coma of a comet. That was called the Discovery Stardust mission, and also from the solar winds, which was the Genesis mission. We have one other sample return mission in work now. You probably heard of OSIRIS-REx. It just acquired a sample from an asteroid, and it is on its way home now. Next slide. So this chart summarizes what we've been involved with as far as exploring Mars. And by the way, when I say we, I'm talking Lockheed Martin Space. We're located here primarily southwest of Denver in Waterton Canyon. So we've been involved with many successful missions to Mars. We built 4 or 5 stationary landers, starting with the Viking missions back in the 70s. Most recently, InSight landed a couple of years ago. And we've also built quite a few orbiting spacecraft. 3 of them are still orbiting Mars today: Mars Reconnaissance Orbiter, Odyssey, and Maven. And then we've built aeroshells for many landers and rovers that have made it to the surface of Mars. Next slide. So for Mars 2020, our role was primarily to, again, supply the aeroshell, which is mainly comprised of the heat shield and the back shell. You can see in the first two pictures there. We also built a helicopter delivery system. So the rover is going to carry, or is carrying, a small helicopter called Ingenuity. Lockheed Martin built the mechanism that will allow that helicopter to be deployed from the rover. We also built some pretty extensive wiring harnesses for the cruise stage and the descent stage, and provided engineering support, logistics support, and we will be also providing telecommunications relays with our orbiting assets. Next slide. So this slide just kind of walks you through what happens when we get to Mars. And the sequence of events takes place, other than separation from the cruise stage, over a time span of about 7 or 8 minutes. So as we approach the planet, we separate from the cruise stage, which is the part of the spacecraft that gets us there. And then and we also eject something called a cruise balance mass device. And what that does is it creates an offset center of gravity for the aeroshell as it enters the atmosphere, and causes it to fly with an angle of attack. And the significance of that is that it creates lift, kind of like an airplane wing, and allows us to steer the aeroshell kind of like how an airplane banks. And so that's really critical to the accurate landing that Steve was talking about. So once we get to the point where we want to be, then we eject another set of balance masses that causes the center of gravity to return to the center line of the vehicle. And at that point, it will fly straight again so that we can deploy the parachute. And then after the parachute's deployed, we're suspended from it. We eject the heat shield, the front part of the aeroshell, and that allows the rover to acquire the ground with a radar, and then the descent stage will separate itself from the back shell. So the descent stage includes what they call a sky crane, which is a rocket motor powered vehicle that gets the rover close to the surface of Mars, and then once it gets to where it wants to be, it lowers the rover down to the surface, and the rover up on a bridle, and the rover cuts the bridle, and then the sky crane can fly off and leave the rover to do what it's there to do. There's also one other really interesting new technology that they're using for this mission, and it's called terrain relative navigation. And so what that does, since this is a pretty rugged area that we're landing in, what that does is takes images of the ground as the sky crane descends, and uses those images to avoid any obstacles. Next slide. So this is a video that we've got that kind of shows that sequence. Okay, so beyond this mission, what's next for us? Steve talked about the sample return mission that we are hoping to be a part of. Really looking forward to that. Beyond that, hopefully the next major step in space exploration is to set foot on Mars. And that's what we've got today for you.
Well, thanks, David. It's great to see how the hardware comes together, especially when it's in our own backyard where a lot of these things are happening. So our next guest is Emily Cullimore. Emily is a mechanical engineer at NASA's Jet Propulsion Laboratory, which is the lead NASA organization for this mission. And she was involved in the engineering of both the aeroshell system, which David has talked about, and the descent stage, which gets the rover safely down to the surface. So, Emily, welcome, and I'm looking forward to hearing about the everything that's been going on with Perseverance over your last 7 years of working on it. So thanks for being with us today.
Yeah, thanks, Steve. I'm excited to be here on such an exciting day. Let me, got a presentation as well. I will share that. So just a little bit about me to start. I grew up in Colorado, in Greeley. I went to school at the University of Colorado, got a degree in mechanical engineering. I'm now in Pasadena, California, working at the Jet Propulsion Laboratory. And I have been here in Pasadena for all 7 years that I've been also working on Mars 2020. A little bit more specifically, I have worked in my 7 years on the cruise stage and the descent stage. As you can see here, the cruise stage contains the propulsion system, all the navigation system, and the solar arrays used to power most of the spacecraft through the cruise phase. And then of course the descent stage, as David was talking about, which is used for the sky crane maneuver to lower the rover onto Earth or Mars. For the last phase of the project, what we call ATLO, the Assembly, Launch, and Test Operations phase. I was the mechanical integration lead for the descent stage and the cruise stage. So with that, and as a mechanical hardware engineer, I spent most of my days in the clean room, which at JPL, one of our largest clean rooms is High Bay 1, just shown here. This is an image from about halfway through our spacecraft assembly process. You can see the descent stage, cruise stage, and rover there on the high bay floor. This is the same high bay that's been used for a number of JPL missions. We've got nice plaques on our wall of fame on the back there. And if you do ever make it to Pasadena, come visit us. We've got a fun gallery you can stand in and check out the spacecraft that we are currently assembling. So my job as a mechanical integration engineer is to plan for, lead the assembly and integration of all of the separate subsystems onto our different stages, in my case, the cruise stage and descent stage, as well as working with the rest of our amazing engineers and technicians to assemble all 5 pieces of the spacecraft together and take the spacecraft through its very important testing steps. This video here just kind of shows a montage of some of that assembly and test work. So yeah, as I said, testing is extremely important. We need to make sure that our spacecraft can survive and support and perform as we expect through the different phases of the mission, from launch through cruise, through EDL, entry, descent, and landing, getting the rover safely to the surface where it can perform its very important job. So looking at a little bit of this testing that we did as part of the mission. First, to test out the launch environment that the spacecraft has to survive. During launch, the launch vehicle ends up shaking the spacecraft. It's really loud, it's really high energy. And so a couple of the tests we do on the spacecraft to ensure that it will survive is our random vibration, which is shown in the top image, as well as acoustics testing, which is shown in the bottom image. Both of these pictures are showing some of our engineers and quality assurance that come in after the test is completed, take a look and inspect all of our hardware, look for anything that might have moved, make sure nothing looks out of place, that visually everything looks okay, along with all of our instrumentation that we have on the spacecraft through these testing steps. Cruise is another environment that we spend a lot of time testing for. On the left you can see kind of what the spacecraft looked like, what it looks like right now as it's cruising from Earth to Mars. Space is extremely cold. It's a vacuum, but you've also got the high energy from the sun shining onto the solar array panels that you can see in the image on the left. And so we are able to test this environment fairly directly using our thermal vacuum chamber. It's shown on the right. You can see that this image shows the spacecraft as we're setting up for this test with our solar light shining onto the solar rays that are on the top of the spacecraft, and one of our technicians gazing up in awe at this very cool test. Some environments are a lot harder to test for. In this case, the sky crane maneuver that David explained is not something that we can test directly. As you may or may not know, Mars is a little bit different than Earth. The gravity on Mars is about 60% lower than it is here on Earth. So it takes a lot more energy to lower the rover on Earth than it would be to lower it on Mars. So when we design the sky crane maneuver for Mars, it's actually not something that would work on Earth. You'd need a lot more power, a lot bigger motors, engines firing on the descent stage to successfully lower the rover down on Earth. So instead of testing the sky crane maneuver on Earth with just one big test, exactly like what will happen on Mars in about an hour, is we break it down into smaller tests. One of the first tests that was done, we called the sky crane full motion drop test. Here's a pretty cool video of it here. This was done on what we call DTM or test model hardware. So this is not the flight hardware, it's stand-in hardware to show us what this drop will look like. This test was really the first time we were able to see, first on MSL, showing that the three bridles that hold the rover and lower them from the descent stage are going to extend smoothly. Along with the three bridles, there's an umbilical cable that's what sends signals between the rover and descent stage until the descent stage flies away, which you can see there kind of bouncing around, as well as showing that the mobility system on the rover, which deploys about halfway through release during the sky crane maneuver. So a very exciting test to see performed successfully. This test was done again on that test hardware, which did allow us to do the test using a smaller rover, less mass to compensate for the fact that, as I was saying, Earth has a much higher gravity than Mars does, but we still need to test our flight descent stage as well, descent stage and rover combined. So to do that, we did a different test on 2020, which we just called the descent stage rover flyaway separation test. In this case, you can see the descent stage, full flight descent stage, sitting on top of the rover. We hooked the descent stage up to a crane, lifted it straight off the rover, and let those three bridles and umbilical cord just unwind to show that they're unwinding correctly, to show that nothing's going to get caught on the bridles. And then in this case, because it is a test, we move the descent stage off to the side and lower it down onto blocks. But another successful test that gives us confidence that our spacecraft, which is almost to Mars, is going to work correctly, deploy the rover correctly. Hopefully we'll see everything go as it did in our testing. So as you can see, hopefully, image on the left, hopefully this is what will be happening really soon on Mars. The rover nicely sitting below the descent stage, almost landing onto the Martian surface. And as Steve mentioned some of those new cameras, which is really exciting to me, especially having worked on the descent stage, are what we call the Rover uplook camera and the descent stage downlook camera. So there is a camera right in the middle. You can see it right there, little black dot, middle of the descent stage that points down at the rover. So we'll take footage of the rover as it's lowering down to the Martian surface. There's also a camera on top of the rover that looks up at the descent stage, so it gets that opposite view. As the descent stage moves away from the rover and eventually flies away, we'll have footage of that, along with another rover downlook camera that's mounted on the side of the rover. Looks down at the ground to see what the surface looks like, especially with all those engines firing, what kind of dust and debris get kicked up, which is a big question that we didn't necessarily have an answer to after MSL. So a lot of good information that hopefully we'll be getting and be able to watch these videos really soon. Give it back to you, Steve.
Well, thank you, Emily. It always amazes me just to look at the hardware being constructed. I guess my mental picture of this is sort of a super Swiss watchmaker with probably a few million parts, but spacecraft are the ultimate in precision engineering and fabrication. So they're just works of art, and I really applaud all the engineers that turn these dreams into reality. And our next speaker in many ways is one of the customers for David and Emily. So obviously the spacecraft have to be constructed, they have to be delivered on site and ready to start doing their scientific mission. But it's the scientists then that, once they're safely where they need to be, in this case the surface of Mars, that they take over the mission and start doing the observations that they went to Mars to do. And so it's a real pleasure to introduce Dr. Mike Wolff. Mike is a senior scientist at the Space Science Institute in Boulder, and he's a member of the science team for Perseverance, and he's been on the science team exercises, science team organizations for basically every rover mission that has been on Mars, starting with Spirit and Opportunity back in 2004, and the Curiosity rover mission, which is still ongoing. So Mike will give us a good overview of the science of this mission and just what it's like day to day to be operating a robot on another planet. So welcome, Mike, and thanks for being with us.
Thanks, Steve. Unfortunately, you've all seen this slide for a few minutes. I hope everyone, for extra credit, found my typo. Usually scientists can spell. I guess I'm an exception. Anyway, we're going to talk a little bit about the science very quickly and talk about the tools, with a particular emphasis with people being one of the main tools in this exploration process. So Steve's already introduced this, but just to show it again, this mission, in essence, is focusing on finding evidence of life, or the building blocks of life that probably existed, now that we have reasonable evidence that Mars was once a different place. And was it actually the image on the left? Well, we like to think so, but it was certainly wetter than what you see on the right. So that is the focus of this mission. And if you need to just sort of sum it up in a question that attracts people's attention, it's just, was there ever life? Was there ever life on Mars? People like to think about, is there life now? Well, that's a harder question. This mission is not really designed to look for current life. Not that if it found something, it wouldn't know, might not recognize it, but it's looking for geological evidence or chemical signatures of the building blocks of life. We're not going around driving into caves or things where the environment might be a little more conducive to life. It's a very harsh place now. So the focus is definitely on what were things like back 3.5 billion years ago or before. So how do they do that? I mean, when you're on a mission like this, there are always very specific goals, and then you talk about how the goals are implemented. But this really can be broken down into two areas. One is the ancient life, signatures of life preserved in the rocks, in the soil, and currently human life. Most of the mission actually focuses on the first one, objectives A, B, and C. I am not a geologist. I study the atmosphere. My stuff is in objective D. A small group of people will be studying the weather and the climate on Mars and understanding the properties so we can do things like predict large dust storms and things that might impact astronauts on the surface. And certainly also, if you want to understand what the climate was 3.5 billion years ago to better understand your geological signatures, you do need to be able to demonstrate you can predict it today. If you can't do it today, there's not much 3.5 billion years ago. So how might you do this? Steve mentioned I started this years ago with the Mars exploration rovers in 2004. Those actually weren't the first rovers. There was a little rover in 1997 on the Pathfinder mission that just kind of drove around. We'll see a picture of what that looked like for scale in a bit. But the MER rovers were definitely more on this concept. How do you do this? Well, the first thing to be able to explore stuff on Mars is you need something on Mars. Well, some people might like to send a grad student, but it's a little bit easier to send a robot. Then you need some scientists. I think some people in program management would suggest you don't need the scientists, but in fact, the scientists are part of it. They provide that we want to go here, our ideas have changed. And in this mission, deciding what samples to take is a very important activity. There are only so many sampling tubes, and Steve showed you what those look like, but there's a finite number of them. So you want to make sure that the things that you put in those sample tubes are the best and most intelligent choices you can make so that when they're brought back to the Earth, they provide the most information. And then, so after the scientists are done and you really want it to happen, you got to make sure you got some engineers in the loop. Steve showed this image, and he suggested I would speak about it a lot, but we don't have time. I'm the last speaker standing in front of you and the Q&A session, which is probably one of the more interesting parts. But anyway, there are two basic types of instruments, and there are cameras, and then there are spectrometers, and you can see the names there. The spectrometers look at a smaller area in many, many wavelengths of light. The cameras tend to look at bigger areas, even if they're zooming, but only at a couple wavelengths. So you like to combine the two to get the best data. The cameras might show you something that looks like it's interesting, and then you use one of the other instruments like the Pixel or even the SuperCam, which has a laser that can vaporize material and then look at the plume for more detailed study. So the scientists have to decide what combination of instruments are going to provide sort of the best information per time or per day on Mars. It's a balance between resources like energy, data volume, how quickly things can get back to the Earth, and if the rover has to drive the next day. It's always a balancing act, and that's part of the discussions that take place. So here's the scale. You can see the one in the middle. This is a copy of the Sojourner, the little rover on Pathfinder in 1997. On the left, you have a model of the Mars Exploration Rover, and these are taken at JPL in front of the cafeteria, I believe. For scale, you see the cameras or the eyes on the Mars Exploration Rover. That's about 5 feet off of the ground, and that rover is about as big as a coffee table in length, a bigger coffee table, and it weighs a couple 100 pounds. So on the right is a copy of Curiosity, and Perseverance is you might call it a build to print copy of Curiosity, but that's just the outside of the rover. The inside is certainly upgraded and has different things on the inside. That's more like a Mini Cooper size. You definitely don't want that to run over your foot. Anyway, but you can see how things have grown in the time period. It's about 15 years between the small one and the Curiosity mission being on the surface of Mars. So a large evolution in a short period of time. So what does this, so here we're going to look at this very quickly. This is what sort of speeded up tracking of the rover might do. You land, you drive to a spot where you think is interesting. Maybe you take a sample, maybe you don't because you decide it's not interesting. You go to another place, and this was a slide from last year, and the actual strategy for where they're going to leave the tubes and how they're going to be picked up seems to be currently still in flux. It's still something they're deciding. So this is one possibility. So you focus initially on collecting samples, and then you drop them somewhere off, the second blue dot. The extended mission means everything's still working great, and we want to go try some other areas. So let's go to a few other spots. You come back, you drop off some tubes, you go somewhere else. Maybe it's a little riskier. So you always go back and drop off tubes before you go on a search for a new region of interest in case something happens, get stuck, something like that, wheel falls off. Okay, wheel's not going to fall off. But anyway, you have to be prepared to have stored the samples you want to send back before you go do something else. So in this process, and this is what's called surface operations, there are 4 general processes going on here. I'm going to check my time. Okay. Strategic, this is the big picture. We want to go to this area and study it. Maybe we'll take samples. And so the strategic mission, aspect of the mission probably focuses on what are those blue circles, these regions of interest. That's what the strategic process would decide. And it could be where we've been before on the surface, but also they'll use data from orbiters. There's been a lot of orbital data of this area. And so the scientists have a pretty good idea of where they would like to go. But once you're there, things can change. And so the strategic plan might be updated continuously. The implementation is a phase where you take the strategic plan and you try to make it a more realizable plan on the scale of maybe 5 or 6 days in advance. So it's still advanced planning, but you're going from just the ideas down to maybe the types of observations that are going to be taken, which instruments are going to be used, and try to apply things you've learned about how the instruments work with the type of rocks or surface areas you're trying to look at. The next step is called tactical, and this is very focused. This is taking the implementation plan and turning it into what's going to happen the next day. And it builds a very specific set of operations for the rover to execute. The rover has autonomous capabilities. In other words, it can detect when it's in a dangerous situation and say, whoops, I'm going to stop. You guys need to figure out what you're doing because you told me to do something bad. But for the most part, it's carrying out a program that is uplinked. They don't let the scientists touch that. That's built by engineers who are specialists in the instruments and the rover movement. So these are all very carefully studied and simulated before the plan is actually uploaded for the rover to execute. And downlink, this is disconnected from the planning process, but it's an integral. This is the part that actually returns the data that's been previously planned to be taken and provides it to the other phases for feedback. You know, this is the data that we took. Did you learn what you wanted? Do you need to do something else? Is this a super great place to take a sample? So these 4 phases operate together essentially in parallel, at least more or less. It's not necessarily always simultaneous, but they are distinct teams that are performing each of these tasks. The other aspect of surface operations, which of course I just gave you in a data dump that was very, very brief, is Mars time. When I started on the Mars exploration rover, it was only expected to live 90 days or 90 sols, which is a Martian day. That would have been mission success. And so everybody was going to be on Mars time, which meant all of our meetings were based on what time it was on Mars at the rover. So we had some meeting at 10 a.m. at the rover that was getting ready to be able to upload the plan, which would happen around noon. And so we were all living on Mars time, which was very interesting, but was a challenge because every day that shift started 37 minutes later. And so your sleep schedule rotates through the day, back through the night. And it was very interesting, but very complicated, especially if you were living in Pasadena, where the JPL engineers are. I was there staying in a hotel without distractions. The poor engineers have to be there and their families are there and they're living on a normal time that's colliding with Mars time. So people have learned that, okay, this is really hard. So for Perseverance, they're going to do it at least 30 days, I've heard, and maybe they'll extend up to 90. It's very important when you're testing systems to be on that local time. You know it's going to do something. It's going to send some data to the orbiter or back to the Earth. So we want to get that right away and act on it. So Mars time has a very specific advantage despite the toll it takes on people. Okay, we're running out of time here. Anyway, we're just about done. So remember, there are these 4 phases that are going on all the time. Even the white lines connecting the regions of interest. These are our rover traverses. Just driving the rover requires planning because maybe you want to take your path a little out of the way to look at a rock that looks cool. Might not be anything, but let's get close and get some data. There's always an ability to replan or to change your mind, just like you would do if you were a geologist in the field on the Earth. You have a plan, you go out, you collect some samples, and you see something that changes your mind, and you suddenly have a new field plan, or at least you modify it. So the same sort of thing is happening with those 4 phases. They're all connected, they're all important, and they're all necessary. So here's kind of a satellite view of what this might look like. Here depends exactly where you land. You know, they know where they want to land, but sometimes you don't always get where you want to go. You heard the previous talks about the guided entry. It can do so much. You can be so much more precise than we were able to be even 15 years ago. So here's a sample plan. If you land where the red bullseye is, you go look at some particular things that you think are super interesting based on orbital data, and then you maybe go somewhere else. But you know, you have this is what a 15-kilometer plan would look like. Or if you land where the green bullseye is, maybe you do something different. There are more interesting things to the left. It's always a decision. It was hard to even choose the landing site, and once you get there, there are just many things that could be very interesting, and it's hard to know in advance. And so that's part of that planning process. Once we're there and people start looking and discussing the data, things are likely to change. And just to close, kind of conceptualize, you're going to only have so many sample tubes. So you would like to get a good distribution of the various types of materials that are interesting if you're a geologist. Again, I have to clarify, I'm not a geologist. I borrowed this slide from a JPL presentation. So these are things that geologists are very interested in, stuff in the bottom of lakes. Anytime when there's water or minerals that they can see have to be there from orbit, like olivine and carbonates. You can see from orbit, from some of the instruments, that those are there. But what's really there? What we've learned on Mars is when you're on the surface, things look different than from orbit. In other words, oh, this area looks like there's a mineral there, and then you drive a rover up to it, and sometimes it's actually hard to find exactly what the orbiter was seeing. So you've got to make a connection, but these are the types of materials that they expect to be interesting from the various discussions on landing sites they've had so far. And that is it. There's so many things you can learn, and I was only able just to give you a tiny peek of what would happen on the surface. I encourage everyone to go to the NASA websites, and there's all sorts of links that can take you to wherever you're interested in learning about something. Thank you.
Great. Well, thank you, Mike. And I guess, are you going to be starting today to switch your day to Mars time once the spacecraft's on the surface?
No, I'm too old for that now. It was fun. It's a lot easier. Like I said, when in 2004, A, I was younger, but B, I was living there and in an apartment. We had blackout shades. I mean, you could really adjust your body. Anybody who's tried, you know, it's been a long time since I pulled an all-nighter. So, but when I am on shift, I will definitely get ready in advance to try to shift my day. But it's hard. If you're only on shift for 3 days and it's the middle of the night, it's tough.
Well, that I guess you get to play the trump card of I'm too old right now, but it's going to be exciting, and this is going to it essentially takes off as soon as the spacecraft's on the surface. So you know, there's this sort of army of people just waiting to jump on this, and it's going to be real exciting.
Yes. Now, what helps make, I mean, the first 20 to 30 days or sols is very prescribed. In other words, they have all these tests to make sure things are working right and that the software that plans things are working right. So there have been many meetings over the last few weeks deciding exactly what activities will take place for the first 2 to 3 to 4 weeks. So there's not going to be as much of this process I suggested about deciding, oh, we want to go there, it's going to be very scripted in that sense. And maybe there'll be the opportunity for some small things to do if there are resources. It'll help that things are very prescribed so people can kind of get used to how this rover is going to operate. Every rover has a different set of tools and a different rhythm with how it operates. And so that has to be learned once it starts. And you can't really know until you start trying to do something exactly how the plan is going to work.
Thanks, Mike. So I'm seeing some questions that have been submitted over Facebook. And for those that are listening, I just want to remind you, you can submit a question in the chat window on either Facebook or YouTube, and they'll get transmitted to us. And for the next 20 minutes or so, we'll do our best to answer them. So let's try and work our way through this. Here's one that I'll take. It's has Mars cooled all the way to the core? And that's something that we really don't know. The Earth, we know, is still molten. The center of the Earth is molten iron and nickel. And we don't know that definitively for Mars, but there is a mission that was launched several years ago. I think it's been on the surface for about 2 years now, called InSight. And its whole purpose is to have a seismometer on the surface of Mars and to be able to understand what the interior is like. So come back in a few years and maybe I'll have a better answer to that question. I guess I'd like to ask a question of both David and Emily, if they're available, is sort of the timeline for putting together your part of the spacecraft. I mean, this is something that obviously takes more than just a few months, and I'm just curious how this fits into your overall career in terms of what fraction of your life has been spent doing this. So why don't we start with David?
Sure. Well, I've been working on these missions for about the last 25 years here at Lockheed Martin. I started in one of the manufacturing areas where we built up the composite structures for them and the composite structures for the aeroshells. We, cradle, I hate to say cradle to grave, but beginning to end, from the point where we are developing a proposal for a mission to the point where we launch, it's usually on the order of about 5 years, I would say. Some are longer. A lot of times because of funding issues. OSIRIS-REx was an example of that. That took quite a long time to develop that spacecraft. For Mars 2020, it was only a few years for us because it was a nearly build-to-print aeroshell from Mars Science Laboratory. So this aeroshell is almost identical to Mars Science Laboratory, just a few minor changes to it. And so the main part of the program for us was only about 2 years long. Of course, there's always some things that you have to start on earlier for, as far as getting long lead materials and things like that. In this case, the ablator material that's installed onto the heat shield, we had to start that a couple of years early to get that process back up and running and get that material made. And that's made by a company called Fiber Materials Incorporated.
But I think one of the things that I always am amazed at is how involved the Denver area is with these missions. I mean, starting back with sort of still the gold standard of Mars missions were the Viking missions back in the 1970s, the first landers on Mars, and those landers were built here in Denver, and virtually every mission to Mars since then has had either building the spacecraft or significant parts of the spacecraft. So
Yeah, you're right. And to be honest, I cannot believe I work in the building that I work in, which is called the Space Support Building on the Waterton campus. It's like a museum here. And you walk around this building and you see all these pictures from all these different missions, including Viking. They have pictures of Viking being assembled in the clean room here, and all the way through to Mars 2020. It's a fascinating place to work.
I'm sure it's gets you out of bed every morning, ready
Yes.
to jump in the car. I'm not sure if Emily is back with us yet. Emily, are you there? Well, okay, she was ducking out to do some background work at JPL before the spacecraft gets there. Here's another one I'd like to direct to Mike. The question was, what happens to a rover when it runs out of power? And you've been in that situation with two of the past rovers, and just what does that do to the people that are involved? And of course, why did it happen is a good story as well. So I'll let you jump on that one.
Well, so many parts to that, but for the audience, basically, when rovers need a certain amount of power to keep things warm. The day to night cycle can be 100 degrees. So, I mean, you can see what happens if you live in a colder climate where you get freezing, like say in the Denver area. That's very harsh on conditions. And so if things are allowed to heat up, cool down, cool up, circuit boards pop up. So you always keep power in the batteries, and there are certain emergency modes. If the power gets low enough, it takes other systems offline so it can run the heaters. So in both cases, Spirit or Opportunity, something happened to produce a low power situation, and it went into this emergency mode, and they never heard about it. Spirit, it was kind of stuck in the sand. It was just starting to get out, but it was becoming winter and the sun was getting lower and lower in the sky, and the solar panels were just not getting enough energy. So at some point it went into this emergency mode and stopped communicating in an effort to preserve power and keep the electronics alive, but it never came back. Opportunity had a much more dynamic demise. There was a global dust storm, and it happened to be in a position where huge plumes of dust, I mean thick, that it would blot out the sun and the sky, came down, and the atmosphere was dark enough that essentially it couldn't get solar power. It too went into this emergency mode. This was the second global dust event that Opportunity had seen, but it happened to be one where dust was very thick. It was very heavy. You can imagine plumes of dust maybe came down, blocked the sun, and coated the solar panels. Nobody knows exactly. They just know it was sending back measurements. They could see things getting dimmer and dimmer, and then nothing. So they imagine how that failure happens. It just can't protect itself. And at some point, when it does get energy on the solar panels, there's nothing left to work. Certainly, it's disappointing to be on the team and everyone's hopes. NASA has a communication protocol. We're going to try to communicate today because it's built in to the rover to have various emergency modes. If it wakes up and it doesn't know what time it is, it communicates based on the position of the sun. If it still has a clock, then NASA knows when it's going to also try to communicate. So all of these situations are sort of planned for, but so far nothing has come back out of that plan.
I guess we should mention that Perseverance and Curiosity are not solar powered. They have essentially a plutonium battery on board that puts out 100-ish watts of power, and they use that to charge batteries and run off the batteries. So they at least don't have to worry about things like dust storms blotting out the sun. So that gives them the likelihood of operating much longer. And I was just reading last night the power system on Perseverance, they believe should be good for about 14 years. assuming something else doesn't give it an early demise. But typically, these spacecraft really outlive their design life by factors of many. As Mike said, the Spirit and Opportunity, they were initially thought they'd last for 90 days, and ultimately we were something like 14 years on Opportunity. Curiosity has been going strong since 2012 and is still a very healthy spacecraft. So let's see, there's another question here about what's the surface temperature on Mars? And I think that's something I'll probably throw at Mike again, since you really worry about the atmosphere, and that has the biggest influence on what the surface temperature is likely to be.
Well, I mean, if you mean just actually what is the temperature of the rocks, it's not as cold as you would think. It can be above freezing if you're sort of near the equator during near a summer solstice. So we always talk in Kelvin, so I have to think about Celsius. But commonly, the surface temperature would be from -20 to 0 Celsius. The problem is the air doesn't retain heat. So if you were standing on the surface of Mars, your feet might be not entirely frozen, but by the time you got to your head, it could be 30 or 40 degrees Celsius, 60 degrees Fahrenheit colder. So you'd need to have much better hat than you would have socks.
I guess one thing I'd like to add is I'd mentioned the answer really depends on where you are, but certainly in the polar regions, in the wintertime, it gets down to below -100 centigrade. We're up pushing -200 Fahrenheit. And it's actually cold enough then to freeze carbon dioxide out of the atmosphere. So you get dry ice, snow and frost and ice on the surface in those areas that are in darkness. So it really varies quite dramatically across the globe. David, we talked a little bit about the Viking missions back in the 1970s, but I understand that things like the aeroshell and the supersonic parachute that is used as part of the landing sequence, those actually have some heritage back to the 1970s with the first missions. Could you tell us a little bit about that?
Yeah, I wouldn't want to speak about a parachute. That's don't think I'm qualified to speak about that, but definitely the thermal protection system on the back shell for Mars 2020 was developed for Viking. It's called SLA 561V. SLA stands for super light ablator, and the V, of course, is Viking. This is SLA is a family of thermal protection systems that are used on a lot of vehicles, including the external tank for the shuttle. This material was developed for Viking and used on the heat shield for Viking. It's a cork and silicone resin-based material, and it has also been used on the heat shield for Pathfinder, Phoenix, and Insight, and on the back shell for Mars Science Laboratory. It's also been used on some of the sample return capsules. I believe the back shell for both Stardust, Genesis, and OSIRIS-REx, I'm pretty sure they all had SLA 561V on them. That's probably the most direct heritage going all the way back to Viking. Of course, the Viking aeroshell was an all metallic structure, and today we build them out of carbon fiber reinforced composites. So that's a pretty big change.
Sorry, I was muted. It's the same facility that the Viking missions were built in that the modern day spacecraft are still being
Yes.
fabricated.
Yeah, the building that I'm sitting in right now, the clean room that Viking was put together in is one of the clean rooms that we still use. Of course, it's grown quite a bit here now, so there's a lot of other facilities here now. But yeah, this is the spot. Yeah, I think there's a spacecraft called Lucy in there right now, being prepared for launch this summer, I believe.
Right, and that's a mission that's going to an asteroid or several asteroids. So,
Yeah, right. I think that's correct. I can't speak much about Lucy. I probably shouldn't have even brought that one up because I'm not very familiar with that mission. But that's the one that we have going today. We're hoping to be part of the Mars sample return program coming up.
great. Let's see. We've got another question here from our audience. What kind of analyses of samples will the rover do? And Mike, I might ask you to jump in on this if you know, but a lot of the different instruments that you showed on that slide are to characterize both the composition and the mineralogy of whatever they're looking at. And so you go from having just an image of the surface where you can characterize say if you're looking at a rock, what the overall structure of the rock is. There's a microscopic imager that allows you to get very close and look at very fine details. And then there's these various spectrometers, including the laser spectrometers, where they vaporize small sections of the rock and measure the gas that's given off. So that tells you what the chemistry of the rock is. And I think there's an X-ray device on the robot arm that gets right up in contact with the surface, and they can tell with very fine detail, like those layers that we looked at in the stromatolites, they can tell what the different chemistry is of each individual layer. So there's just a whole host of those sorts of observations that can be made. And Mike, I think you're more familiar with how that all comes together with planning a sequence, but maybe you can elaborate on that.
Hey, Steve, before you dive too deep into that, I'm going to need to step away. I just wanted to thank you for having me on today.
Okay, well,
It's a pleasure.
thanks, and we look forward to seeing your aeroshell get us through the atmosphere. So
Yes, very much looking forward to it. Thanks again.
Thanks, David.
Well, Steve, I think this is revenge for I'm not a geologist statements, but the one thing I would say for the viewers, the audience, are that each of these instruments tends to look at a different aspect of the composition. Some might look at the actual materials, the chemistry, the minerals. Others look at the elements that make these up, right? Often you only have one view or another. If you're looking at the minerals, you're looking to see how light is reflected, and sometimes there's less light reflected in certain wavelengths. That can be like a fingerprint to what the mineral is. But sometimes you're only seeing the surface. So when you look at something that gives you more elemental abundance, it might go deeper into the rock or into the surface. So not only does it look at maybe the components versus the actual molecule or mineral, but it says, was it the surface of the rock or deeper into the rock? And that's kind of the limit of my knowledge of this as an atmospheric person.
Okay, well, thanks, Mike. I guess the one thing that the atmosphere contributes is dust, sort of raining out of these dust clouds. And so that's something that the geologists that are trying to determine the composition of the rocks really have to worry about. You need some way to remove the dust. And, past missions have used little wire brushes. I think Perseverance actually has some pressurized nitrogen canisters where they blow the dust off of the areas. So it's not quite as simple as just doing it on the Earth when you're 200 million miles away. I think we're very close to where we were going to move off to NASA TV. So for our audience, we're going to switch to the live coverage from NASA, and things start happening very quickly, just about 7-8 minutes from now, and then the final 7 minutes of terror, getting the spacecraft softly down onto the surface, will commence, and we expect that about 5 minutes of 2 Mountain Time is when the landing will occur. So we'll be coming back for more Q&A after the landing, a little bit after 2 o'clock. And the one thing I just wanted to end with is what we're going to be hearing today. And I mentioned in my presentation that there are multiple spacecraft in orbit around Mars right now, and we use those. Sorry, I need to get the full screen here. We use those to communicate and act as communication satellites with Perseverance. And so on our upper left here is the Mars Reconnaissance Orbiter, and on the right here is the MAVEN mission. And both of those spacecraft will be within sight of the Perseverance entry capsule as it's coming into the atmosphere. And so Mars Reconnaissance Orbiter does what's called a bent pipe. It receives the telemetry coming in from the entry system, and it transmits it directly to the Earth with about a 16-second delay or so. So we'll be getting live telemetry that way. MAVEN will be recording the telemetry stream and then playing it back about 10 hours after landing. So that gives us a duplicate set of that information. And in addition to that, from the Earth, we can hear what are called carrier tones from the descent system. And imagine, when you push a button on your telephone, you get a certain tone of the beep from the telephone. The same thing happens with the entry capsule as it's going through the Martian atmosphere. You get a different tone when it's at maximum heating, when the parachute is deployed, when the heat shield drops off, when the sky crane starts, and then when the spacecraft touches down. And so there's multiple ways to get the information. And we'll be hearing all of that. But the other thing to keep in mind is that it takes light about 11.5 minutes right now for the radio signals to get to us from Mars. So everything, when we say it's landed at 1:55, it's actually been on the surface for about 12 minutes already at that point before we even know what's happening. And so this is all automatic. It's programmed on board, and we're just going to be sitting back and waiting for the call out that the spacecraft is on the surface of Mars. So thanks for being with us, and I think we're going to switch off to the NASA feed at this point. If anything real exciting happens, I'll jump in just with a call out. But with that, I think we're just going to switch it over to NASA. So thank you.
Excited about space, and I think it's the same reason that many others are excited about space, and it's that the people in the space industry work to answer two of the biggest questions that humans have ever asked. Are we alone in the universe, and where did we all come from? And by sending a rover to Mars, we are gaining evidence for the answers to these questions, more evidence than we ever had before, and I think that's so exciting.
It is, and I know you get loads of interesting questions from kids. Have you gotten any about Mars specifically?
Oh my gosh, yes. Everybody loves Mars. It's in movies and books and TV shows, and everybody loves Mars. So one of the things that I get asked a lot is that, it's called the red planet. Why is it red? Well, it's red because it's literally rusty. The top layer of soil on Mars has iron oxide in it, or rust, and rust has that brownish red color. So it's red because it's rusty. And also because it's red, they ask, is it red hot? Is it really hot on Mars? And well, no, actually, it's colder than the Earth. It's farther away from the sun. So as you would imagine, it's a little bit colder than the Earth. It also has a really thin atmosphere. So the heat that it does have, it has a hard time keeping in. And so it's a little bit colder. But then I also get asked, what would I weigh on Mars? That's a really fun question. So on Mars, it's a little bit smaller than the Earth. So the gravity there is weaker. It's about 3/8 the gravity that we have here on Earth. So if you weighed 100 pounds here on Earth, you'd weigh 38 pounds on Mars, or 100 kilograms here on Earth, 38 kilograms on Mars.
Those are all super fun. I think even some adults want to know the answers to those questions, Emily. Now, why do you think it's so important to educate kids about science and give them that great foundation?
Well, science is the language of nature, and learning about science and learning how to think like a scientist means you are learning how to systematically seek out truth in the world. You are learning the scientific method. You're learning how to be a critical thinker. And honestly, those skills are great for whatever you end up wanting to do in life.
True. If you want to be a scientist or an opera singer, that holds true. And what are you most excited about today?
I mean, humans are launching a robot to Mars. That doesn't happen every day. I think in all of the hecticness that is going on today and all of the nerves, I just hope everyone can take a moment to sit back and remember that we live in a time when humans have the ability to send a robot to another planet. And that's so cool to me.
It is very cool, Emily. Take a deep breath. Thanks for joining us here.
Thanks for having me.
Sending it back to you now, Raquel.
Thanks, Marina. We are offering lots of ways to ride along with us to Mars. Now put yourself right into the action now with our Perseverance photo booth. You can pose next to the rover, place yourself in our mission control, and even see what you might look like taking a selfie on the red planet. There, you'll also have a chance to sign up to send your name to Mars on NASA's next flight to the red planet. It's all available at go.nasa.gov/Mars 2020 Toolkit. And joining us now is JPL Chief Engineer and landing veteran Rob Manning. He will be breaking down key moments coming up, and very few people know more about landing on Mars than Rob, going back to the Pathfinder mission in 1997. Thanks for joining us today, Rob.
Thank you very much, Rick, for having me here. And what a wonderful experience. What a wonderful day for a beautiful day in California. We're just also excited here, anxious, worried, but very hopeful.
Rob, I have a question for you. There is a landing tradition at JPL that involves eating peanuts for good luck. Can you tell us how did that start?
Yes, it started in the mid-1960s. What happened was we had a series of missions that had failures. The Ranger program in the early 1960s, one after another, failed. And what happened was one day, a fellow by the name of Dick Wallace on Ranger number 7, on the 7th attempt, decided to bring peanuts to the ops area just before the launch. And guess what? That mission worked. Now, we're not supposed to be too superstitious. We're engineers and scientists after all, but we love tradition. And ever since then, before launch and before critical events like entry, descent, and landing, we have brought out peanuts and shared them with the team. And it's been really a wonderful little experience. And so this is something we will do. We're doing right now. And it's something that we just can't help ourselves. It's just part of the experience.
Oh, well, speaking of the experience, how did the Perseverance team keep the tradition alive this year?
Well, this year we're passed out little packets of peanuts to the team, and they can sneak one peanut in their mouth as part of to keep the tradition alive. But this is part of the COVID experience, but we can't leave this one undone. So this is what we're doing, and this is going to help us land safely.
All right, thanks, Rob. I have some questions for you a little later on, but we're heading back to Swati Mohan, who is part of the landing team. She'll be calling out key milestone and events as they happen from Mission Control. So let's listen in right now.
So right now we're still about 20 minutes from entry, and the EDL phase is giving a last-minute confirmation of what will be happening in the upcoming changes to the vehicle, just to remind the team.
And this will allow us to steer our trajectory as we make our way through the atmosphere. This is one of the things that allowed MSL, the Curiosity rover, to land where it did. And we're depending on the same type of entry guidance this time around to help get us very close to our target. As we make our way through entry, finish our guided entry profile, we'll do a maneuver called heading alignment, where we point toward the target and get ready to deploy the parachute. But before we deploy the parachute, we need to get rid of a set of balance masses that have been giving us a center of gravity, or CG offset, throughout the guided entry phase. So these are called the entry balance masses. We also call this maneuver SUFR, S-U-F-R, or straighten up and fly right. So we'll go ahead and eject those masses when we get a trigger from the GNC system telling us that we're at the appropriate range to the target to do so. As soon as we deploy those, we will no longer have a CG offset, and we'll be ready to deploy the parachute 17 seconds later.
Right where the Perseverance team is sitting now, what's in store for them as we approach landing?
I'm going to hold here for EDL prep as we're about to start that anchor.
Copy, piece 2. And activity, please call that out when it's ready. Copy, Flip.
Can you make the announcement now? Go ahead. Magnus, make the announcement that...
All right. Now, Rob, you've been right where the Perseverance team is sitting now. What's in store for them as we approach landing?
Well, this is the nail-biting time. Fortunately, we still have ones and zeros coming, but very soon, as we approach cruise stage separation, the transmitter on this rover we've been using all the way to get to Mars is going to be turned off. So we will lose our ability to see ones and zeros. But the good thing is, once the cruise stage is gone, there's another radio that will continue transmitting a tone, so that like a flashlight, that will allow us to at least see that the vehicle is still on, and that color of that flashlight tells us a little bit what state the rover's in. But soon after that, it won't be very long before we'll be able to hear more ones and zeros coming from the spacecraft. So this is a really exciting time, and it's just important to remind people there's a lot that can go wrong in a day like today. There are thousands of things that have to go right.
Yeah, we had success in the past landing on Mars. You'd think it gets easier, but it really doesn't. Why is it still so difficult?
Well, because it's involved thousands and thousands of things, hundreds of thousands of lines of code. There's 79 pyrotechnic devices. Each have to work perfectly. One critical wire short, or one key thing, mechanism that doesn't work or breaks, and it's mission over. And so it's, and it's very easy. We're human beings. We're not perfect. Mistakes can be made. We count on each other to find our own mistakes, and we work very hard to learn from the mistakes of the past. We've had many failures. Remind people, roughly half, around half of the missions to Mars over history have failed. And so that could happen today too. Even though we've had a nice, wonderful string of successes in the United States, it's still still a bit of a gamble that we have hoped that we have erred in the side of luck. And we've stacked the deck and loaded the dice to make this thing succeed. But if we do fail, and something bad happens today, I can tell you, we're going to learn it. We'll have the data that tell us what happened. We'll know why. We'll figure it out. And if we are allowed, we will pick ourselves up and get us back on the horse. And if Congress and NASA allow, we will try again. As we always do, we will learn from our mistakes.
And what are the possible scenarios we could be looking at today?
Well, there's things like one of the key stressful elements for all of us is parachute inflation. But just even separating from the cruise stage is a pretty major event. Lots of devices have to work properly. Certainly, the heat shield separation, getting the descent engine started. There's no less than 16 rocket motors that have to work. 8 to control during entry, another 8 to control it during landing. I said, it's a lot of stuff, and it all has to work. And guess what? We haven't done this before with this vehicle ever. This is this first attempt to actually land. We can't try this on Earth. We can't do, we don't have test pilots to try it out on this planet before the big show. So this vehicle is doing it for the first time. We've done the best testing we could do in bits and pieces, but you know, it's as best as we could do. But I think our team is up to it. This team is the best. It's a diverse, intelligent, amazing group of people. People from all over the world who worked on this, not just here in California, but all over NASA, contributors from aerospace, universities, countries around the world. It is just an incredible, remarkable engineering achievement, and I am just so proud of this team.
Thanks, Rob. Now, let's listen back into Mission Control.
Flight, we're about 14 minutes from entry interface. The vehicle is currently preparing the heat rejection system that has kept the thermal system cool inside the air shell for about the last 6 months. This will allow the spacecraft to more easily cut the line in upcoming cruise stage separation, which is under 4 minutes now.
We have now enabled the Rover Pyro Bus.
That's the pyrotechnic system that's
We're
going to
powering off the cruise stage devices.
And these are the things in the cruise stage that we no longer need. With the pyrotechnic system working, we can explode the devices.
The vehicle is preparing for the upcoming cruise stage separation in about 3 minutes 15 seconds by powering off all the devices on the cruise stage in order that they can be safe once the cruise stage is jettisoned.
Yeah, this cruise stage has been very reliable.
We are firing our first pyros to vent the HRS liquid and gas.
This has been the coolant that's kept their vehicle from getting too hot on the way to Mars. We have to vent it into space. And this is one of the first major events that take place as part of entry, descent, landing.
The HRS vent anchor is complete.
Yes.
We will see the next anchor in approximately 3 minutes.
Okay.
We are currently 12.5 minutes from entry interface. We are coming upon cruise stage separation in 2 minutes and 20 seconds.
What's happening now, Rob?
Okay, well, we're just waiting. The rover is completely in charge. It's doing all the things we've taught it how to do. It's all built into the software. We've tested it over and over and over again. This team has spent 24 hours a day, 7 days a week, testing this thing for years. And so this is really the culmination of all that work. So this vehicle is getting ready to push that cruise stage away. Once it gets pushed away, the entry system with the rover inside, with the rover still in charge, is going to get ready to take the vehicle, turn it to the right orientation, and aim it to Mars and prepare for entering the atmosphere. This won't be long. Be prepared for this event.
We're about 1.5 minutes from cruise stage separation. About 11 minutes, 20 seconds from entry interface.
Okay, so it's about 10 minutes from cruise stage separation till entering the top of the atmosphere. From then on and out, things happen
We're
fast.
switching to MFSK tones. Telemetry will have stopped.
Telecom is confirming that the spacecraft has switched to broadcasting tones. These tones are received directly from Perseverance, but have very limited information content. We won't receive real-time information until about 9-10 minutes from now, once the Mars Reconnaissance Orbiter starts relaying information from Perseverance. We are under a minute from cruise stage separation, about 10.5 minutes from entry interface.
It's getting exciting. I have to admit, I am quite anxious, but very hopeful that this machine is going to do what we asked it to do.
You're seeing the heartbeat tones.
Okay, that means that there's no more ones and zeros coming. It's just the vehicle telling us it's still alive.
We're continuing to receive tones from Perseverance, standing by for cruise stage separation.
Yes.
We have indication that cruise stage separation has been confirmed by the spacecraft.
We're off on a good start.
In about 1 minute, Perseverance's landing software will wake up and begin the final preparations for entry. The first action it will do is to fire warm-up pulses with its entry thrusters. These pulses ensure that the spacecraft gets the thrust that it wants during entry interface. We're about 9 minutes from entry interface.
Okay, so now the vehicle's on its own. It's turning itself into the direction of facing the heat shield toward Mars, and will eventually hitting the top of the atmosphere. We're not far away. This is going to go very quickly from here on out.
That's confirmation that we got shadowed by the cruise stage as it passed through our beam to the Earth.
Telecom indicated actually that we could see a signal that the cruise stage went between the Perseverance entry capsule and Earth. So we saw a little blip, the data stream indicating the cruise stage separation. We have confirmation that the vehicle has started warming up those entry thrusters. Warm-up pulses have begun. At this point, the spacecraft is trying to stop its spin from the cruise 2 revolutions per minute down to 0, and then will turn to its desired orientation from entry. It will separate the 2 balance masses that has kept it balanced during all of cruise. This will allow the entry capsule to have lift when it enters the atmosphere. We have confirmation that the spacecraft has turned to the desired entry attitude. We're about 7.5 minutes from entry interface.
Okay, the vehicle is pointed in the right direction. The thrusters are warmed up and doing their job. And now we've spun down from the 2 revolutions per minute that the vehicle had the whole way to Mars. It's a spin-stabilized spacecraft. And then from here on out, it's going to just be a bullet, and it's going to control its orientation and attitude via rockets on the back of that back shell.
Points carrier lock. Sorry, the DTE from Radio Science from Green Bank reports carrier lock. You see the carrier on the downlink.
Flight level 1.
We are continuing to wait for entry interface. We're about 6 minutes and 45 seconds from entry interface. We have confirmation from Greenback that they are receiving direct-to-Earth telemetry via that path. The spacecraft Perseverance is currently transmitting heartbeat tones. These tones indicate that Perseverance is operating normally and has nothing significant to report. This is as expected. We're currently just over 6 minutes from entry interface.
Okay, and now we wait. soon as we get to the top of the atmosphere, it'll be very quickly, which is the entry point. It won't be very long before the atmosphere will start getting thicker and thicker. It's going very quickly at a fairly steep angle of 15 degrees into the atmosphere, and as it starts to slow down.
We're just under, we're about 5.5 minutes from entry interface. We're still receiving heartbeat tones. We expect to continue receiving heartbeat tones until about 5 minutes after entry. At that time, Perseverance will be no longer in view of our antennas here on Earth. About 90 seconds prior to entry, the Mars Reconnaissance Orbiter should begin receiving telemetry from Perseverance and streaming it to Earth in near real time. There are a few expected short outages, such as when we have a plasma blackout or when we enter the peak heating phase. Aside from these outages caused by the plasma blackout, antenna switching, or high dynamic events, spacecraft events, we should have telemetry until about 90 seconds after landing. A plasma blackout is when the signal from Perseverance isn't strong enough to make it through the superheated, super fast air flowing around the spacecraft all the way down to Earth. Once the temperature drops below that peak heating, we do reacquire the signal from Perseverance. We are currently about 4.5 minutes from entry interface. Perseverance continues to report heartbeat tones, indicating everything is nominal.
Okay, what we're looking for now is Mars Reconnaissance Orbiter should be in view soon of our vehicle and be able to listen to ones and zeros coming from a separate radio that's really designed to talk between spacecraft.
MRO reports the electro radio is powered on, ready to receive signals from the lander.
Okay, MRO is ready and able and waiting for to hear from our rover.
Mars Reconnaissance Orbiter has reported that it's ready to receive the signals from Perseverance. It should be in a few minutes here. We're just
Flight Local 1
from entry interface.
We don't need these ones and zeros, as Swati said, but to land safely, but we really need it for our own health and well-being today to keep our nerves under control. But
around this time, a second spacecraft, Maven, should begin picking up telemetry from Perseverance and will continue to record that telemetry until several minutes post-landing. We won't get that data for several hours after landing as it's being recorded and then will be forwarded to Earth later. We are continuing to receive heartbeat tones, indicating that everything is nominal. We're currently at about 3 minutes until entry interface.
okay. Very soon we'll be getting ones and zeros, I hope, from our radio on the rover. The entry interface is nothing more than just an arbitrary place in the sky that we've defined to be above the atmosphere. But from that point on, there's definitely atmosphere, and above it there isn't.
We are 2 minutes from entry interface. Perseverance is to transmit heartbeat tones, indicating everything is nominal.
So the tones can tell us whether something is bad or not is happening. So far the heartbeat is doing well. So the vehicle thinks it's in good shape to land, which is a great sign.
We're just under 2 minutes from entry interface. As it gets closer to Mars, Perseverance is actually being pulled in by gravity and accelerating. By the time Perseverance reaches entry interface point, it should be going just under 5.4 kilometers per second. We're at about 90 seconds from entry interface and standing by for Mars Reconnaissance Orbiter to pick up the telemetry. We are 1 minute from entry interface.
Those are in receive mode.
We have confirmation that the Mars Reconnaissance Orbiter is now relaying data from Perseverance. We're about 30 seconds from entry interface. Perseverance is going about 5.2 kilometers per second and is about 190 kilometers altitude above the surface of Mars.
Confirm UHF data flow.
About seconds from entry interface. 5.3 kilometers per second and an altitude of about 150 kilometers from the surface of Mars. We have confirmation of entry interface. Perseverance is currently going 5.3 kilometers per second at an altitude of about 120 kilometers from the surface of Mars. The spacecraft is now waiting until it begins feeling the atmosphere of Mars to slow it down. Once there is enough atmosphere, it will start controlling its path to the landing target. Navigation is also confirming that we can see a little bit of that slowdown of the atmosphere on the Perseverance entry capsule. Our current velocity is about 5.36 kilometers per second and an altitude of about 67 kilometers from the surface.
We are probably seeing MRO plasma blackout at this point.
The vehicle should be doing its turns right now.
MRO has lost lock.
Perseverance. We have indications that Perseverance is now performing bank reversals in the atmosphere. These are the steps in order to control its distance to the landing target. Perseverance has just passed through the point of maximum deceleration and has indicated that it felt approximately 10 Earth Gs of deceleration.
MRO has lock again.
Yes, 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 yes.
We saw a small outage of the UHF telemetry from Mars Reconnaissance Orbiter during that peak heating phase, likely caused by the plasma blackout. Perseverance is still continuing to perform bank reversals in the atmosphere to control its distance to the landing target. Perseverance is going about 1 kilometers per second at an altitude of about 16 kilometers from the surface of Mars. We have entered heading alignment, which means Perseverance is no longer trying to control the distance to Mars, but to the target on Mars, but instead is flying straight to the target.
Parachute.
Our current velocity is about 550 meters per second at an altitude of about 15 kilometers from the surface.
MRO is reporting good telemetry log.
We are coming upon the straighten up. We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Yes, yes, yes.
The navigation has confirmed that the parachute has deployed and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars. Perseverance has now slowed to subsonic speeds and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Yes, yes, yes.
Perseverance now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers of the surface of Mars. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
Almost there.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Yes.
We have priming of the landing engines. Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN Safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver.
We've lost direct-to-earth tones.
As expected. As expected.
Sky crane maneuver has started. About 20 meters off the surface.
We're getting signals from MRO.
UHF is good.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life. At this point, the descent stage has flown away to a safe distance. Perseverance is continuing to transmit direct through Mars Reconnaissance Orbiter to Earth.
Oh my God. Oh.
MRO reports they're still getting telemetry from the lander.
All right, all stations.
We got it.
Touchdown confirmed. We're going to wait for the images.
Wow.
This is so exciting. The team is beside themselves. It's so surreal. Stay tuned. We might get some pictures.
That'd be great.
So much has been riding on this.
Yeah, we just heard the news that Perseverance is alive on the surface of Mars.
It's not the
Flight, we have seen the completion of EDL 3000. Copy activity. That is as expected.
MRO is still seeing a strong signal from the lander.
We have just heard the news that Perseverance is alive on the surface of Mars. Congratulations to the mission. And looks like we have some more news in. It looks like we're getting the first image. Here, take a look at the first image.
Flight, this is OL3. I have the target point on the map when you are ready. We are ready, OL3. Go for it.
Wow.
All right. We'll take it. We'll do it.
Flight, I'll be moving in, showing you the safe zone that we've landed in.
Just put the first image from Perseverance on the surface of Mars. Now, it comes from the engineering cameras, known as the hazard camera. This camera is mainly used to help the rover drive safely around Mars, and we will get higher resolution photos later in the day.
Look at that, right? You get the safe.
Wow. Let's see our engine. Nice.
This is amazing.
Here's Andrew.
For Steve. Stand by for Steve.
Yeah, I'm not. Oh my God.
You did it. You did it. You did. You led the team. You made it happen, man. Congratulations,
We just got our second image in. Our second image is in.
Okay, these we have a camera in the front and rear of the spacecraft. They're near the ground, so these are pretty close. So you can see the wheels there, and they're a little dirty because we've got glass covers over these cameras. But we took these seconds after landing, so there's still dust in the air from our landing event. So this is happening. This happened just seconds ago. Just arrived, and this is really amazing. And we even know where we landed. This is the most amazing thing. The vehicle has told us where it's landed because it figured it out. You know, this is a sign. NASA works. NASA works. And when we put our arms together and our hands together and our brains together, we can succeed. This is what NASA does. This is what we can do as a country on all of the problems we have. We need to work together to do these kinds of things and make success happen.
And joining us now is the acting administrator of NASA, Steve Jurasik. Steve, welcome and congratulations.
Hey, thank you. What an amazing day.
How does it feel to have another rover on Mars?
It's amazing to have Perseverance join Curiosity on Mars, and just a credit to the team. I mean, just what an amazing team to work through all the adversity that goes and all the challenges that go with landing a rover on Mars, plus the challenges of COVID, and just an amazing accomplishment.
And what does this mean for NASA and its future plans?
So for robotic exploration, every time we execute a mission with new instruments, we discover new things and things we never thought we would discover. So that always informs our future robotic missions, both landers, rovers, and orbiters. This mission also has technology on it. One of the cool things is the Ingenuity helicopter. It's an experiment on this mission, but if it's successful, we can use it as an science observation platform by putting instruments on it, and also use it as a scout for future rover missions. And then just the entry, descent, and landing capability. It'll allow us to land more larger, more ambitious robots on the surface of Mars. And then for human exploration, we have the MEDLI, Mars Entry, Descent, and Landing Instrumentation, which is going to give us EDL information. We have the Mars Environmental Dynamics Analyzer. It's going to give us size and properties of dust particles, because when we send people, we're going to have to deal with that dust. This is just an incredible mission because of the science and the technology, and then caching samples for our Mars sample return mission. That will be an amazing mission, the first round trip to Mars and back, and bringing those samples cached by Perseverance back to Earth to examine with state-of-the-art equipment in our laboratories here on Earth.
We have so much to look forward to. And we also have a student question coming in from Landon. Let's take a look.
Hi, my name is Landon Applegate. I'm in 6th grade, and I'm going to Academy for Academic Excellence. And my question is, do you think we could get resources from Mars to help on future missions, or even as like a launching point?
Great question, Landon. Actually, we have an experiment called the Mars Oxygen In Situ Resource Utilization Experiment, or MOXIE, and it's going to demonstrate generating oxygen from atmospheric CO2, and that could help generate breathable oxygen, and even if we can liquefy it, oxidizer for propulsion systems. So that's a tech demo on Perseverance. And then we're going to continue to characterize the frozen water on and below the surface of Mars, and eventually try to figure out how to extract that water from the Martian soil, or what we call regolith. And then we can use that for potable water, and also break it down into oxygen and hydrogen for rocket fuel. So absolutely, we're going to try to eventually figure out how to live off the land to support human missions to Mars.
Thanks for taking the time to talk to us today, Steve.
Thank you.
And now that Perseverance has safely touched down on Mars, let's learn more about what's in store for the rover. Joining us now is Surface Mission Manager Jessica Samuels. Jessica, your surface operations team has now taken over. What are they doing now?
Yes, hi Raquel. We are so excited here in the Surface Mission Support area. The team will do a handover with the Entry, Descent, and Landing team and pass any critical information. And then this team behind us will be the team that does the health and safety assessments daily as we progress on this mission.
And what do the upcoming weeks look like for your team?
So as we enter Mars time now, the commanding team will be working overnight while the rover is asleep, so that we can perform the initial checkouts of our key rover functions and our science instruments. And we have to do this all in time for the regularly scheduled communication pass, which happens in the morning. And so we will be working around the clock, making sure that Perseverance is healthy, and we will begin this exciting adventure.
And can you tell me, what's it like living on Mars time?
It's a little bit like constantly, flying and changing your time zone. The rover, on Earth, the rover wakes up at the same time every day, but on Earth, that's 40 minutes later. So the team is going to be shifting our work schedule by 40 minutes as we come into work over the next few weeks. So it'll be exciting and some late nights, but we're also excited, and we can't wait.
It's a whole new lifestyle.
Yes.
We also have a student question for you. This is Sophia's video.
Hi, my name is Sofia Lopez, and my question for NASA is, how's Perseverance gonna survive? And here's a drawing that I made from Perseverance thinking about Earth. Thank you.
Well, Sophia, Perseverance survives with a power source that charges its batteries overnight while it sleeps, and it keeps heaters on so that all of our critical electronics can stay warm, as well as our mechanism. But it's really survived by the team that performs the health and safety assessments every day and communicates with the rover and makes sure that she's doing okay.
Well, thanks for your time, Jessica, and good luck living on Mars time.
Thank you. Should be fun.
Let's head back to Marina as she gives us a sneak peek into the future at JPL.
Thanks so much, Raquel. It's definitely bustling behind me. It's not quiet like it was just 20 minutes ago. And congrats to the whole team. What an amazing accomplishment. Mike Watkins is the director of NASA's Jet Propulsion Laboratory. He was the mission manager during the Curiosity rover landing on Mars. Welcome, Mike.
Oh, thanks. Glad to be here. You can see all my mask markings soon.
Well, we've done it. We're back on Mars. This is, it's amazing how different it feels with the COVID precautions, but obviously, Emily, you're smiling. Mike, you should be smiling. You've got a job for the next decade. And Emily, what was it like there at JPL, seeing all the folks you've been working with on this mission?
Oh man, it was just amazing. I know a lot of the folks I work with worked on Curiosity as well. So this is their second landing, but it's indescribable right now. I know I was on a web call with some of my colleagues as well, and especially with that first image coming back, just unbelievable. We're so excited.
Well, congratulations. Everything you worked on worked perfectly, and now your job is over, I guess.
It is. I happily will hand the reins over to the rover team, Perseverance.
So, Mike, were you on the edge of your seat, waiting to hear all the call outs and see that it was actually still alive?
JPL makes it look easy, but I know they're all on pins and needles as well. It's worked hard, it's been tested, but there's nothing like seeing it actually work. And getting the signals back and the excitement builds. And then the first picture, it's, everything says it's there, but till you get that first picture, I don't think it sinks in.
I guess I should explain those first couple of pictures. They're from the cameras that sit down looking at the wheels of the rover to help plot out their path when they're driving. And what we got back was a thumbnail of each of those. So very, very reduced resolution version. And those cameras, since they're low and subject to getting dust all over them during landing, they have a little cover glass that or a lens cap that is over them. And so you can see that they look really dusty, but over the course of the next hour or so, I believe those cover glasses get popped off. And so the next images will be much, much, much better, as well as higher resolution. And those should be coming in later this afternoon, from what I understand. Go ahead, Emily.
I believe I heard it'll take maybe a day or two for the video as well, but within a couple hours we should have high resolution photos, and in a couple of days we should have some great video that we've never seen before.
Yeah, I think we mentioned this with all the cameras on board. I think there's 3 cameras pointed up at the parachute when it deploys, and there's cameras pointed down watching the ground approach, and then cameras on the rover looking up as it's descending on the sky crane. And it's going to be amazing. And just, you can't make this stuff up. It's just so impressive to see it in action. I think if we're seeing the NASA TV feed on our screen, we had a question that came in right before landing about this helicopter that is part of the mission, and I think that's what we're seeing on the NASA TV. But this is an engineering experiment that they're really just trying to, if they can fly in the thin atmosphere of Mars, and if something like a drone capability where you could look over the next hill, for example, and plot out your course better, will be useful. And so I think the way this is going to work is over the next month or so, the rover will be selecting a very flat spot that they can drop the helicopter off. Right now it's attached to the belly of the rover, and so once they do that, then the rover backs off about another 100 meters or so, a football field, and over the course of the next month they take 4 or 5 test flights with the helicopter, and I think each one they'll get maybe 5 or 6 meters off the ground, so 15-20 feet, and they last a maximum of about 90 seconds, and then they come down and the batteries get recharged by the solar panel, and they try again. So it's going to be another very photogenic activity very early on in this mission, and something that I'm sure, especially the school kids out there that likely got drones for Christmas in their Christmas stocking, that they'll be very excited about. So, Mike, what's next in terms of ramping up the science team? Are you folks going to be Zooming continuously for the next multiple days, or do you get time off while the engineers make sure everything's working?
Well, certainly the science team begins to participate in the process. Even though things are quite scripted, they still go through the planning process. I believe, in other words, the implementation phase that I mentioned briefly in my presentation for SAW 1 actually starts today. Today is SAW 0, so they start doing the implementation plan for SAW 1. And so the process is getting exercised and tested, even though there have been special activities before landing to do this. Nothing replaces being on the surface of Mars and seeing how everything works. And like I said, so the science team will be involved. The science team staff certain ops positions. The ops teams, the JPL engineers are certainly involved in their positions. So everything is ramping up. But it's, again, it's scripted, so it's a controlled ramp up.
Well, I expect there's some serious cork popping going on across the world for both the science team as well as all the folks like Emily and David that have spent many years of their lives getting to this point. So, Emily, how about at Lockheed Martin? Is there? I guess with COVID, there can't be dancing in the hallways, but I would imagine there's a lot of very happy people there.
Yeah, no, at JPL, we've definitely got, our small team on lab who are ecstatic, and we've already, the team that is working through the cruise phase is different than the landing team, which is different than the actually on Mars rover team. So I know they've been handing the ball off, and everyone's excited to get started. And even from afar, it's not quite the same as if we were all together. But I think the excitement's still there. Yeah.
Well, lots of people deserve high fives for sure. As Mike said, this looks easy and routine, but this is right up there with the hardest things that humanity ever even attempts to do. And success speaks for itself, I guess. It's a job very well done. I should mention that the main screen that we're watching here is still what's coming in from NASA TV. So we're just trying to, for the next 10 minutes or so, field whatever questions that our viewers, our viewing audience sends us in. So we'll try to take care of those. I guess one thing that we didn't talk about earlier is that Perseverance is actually the third spacecraft in the last 10 days to arrive at Mars. There was one from the United Arab Emirates, the Hope mission, and then the Chinese space agency also has a spacecraft in orbit at Mars right now, and they're expecting to land in April or May. And then that lander also has a small rover on board. So it's getting crowded at Mars. And that's in addition to, well, I forgot to count before we started, but there's something like 10 or 11 spacecraft operating at Mars right now. So lots of things to keep track of with all these different missions. Mike, you actually have spent a lot of time and played a very important role on the UAE mission. Could you tell us a little bit about that?
Yes, that is a mission that is more like a weather satellite. Its goal is to observe the atmosphere and the connection between the top of the atmosphere and the lower atmosphere over multiple timescales. Previous missions have tended to look at the atmosphere or the surface at the same times of day, like mid-afternoon. Most US orbiters are in what's called a sun synchronous orbit. It's always about 2 to 3 o'clock p.m. or 2 to 3 a.m. underneath the orbiter as it passes over. The Emirates mission will be looking at the surface and the atmosphere at different times of the day over the whole planet. So over a 10-day period, for example, it's going to capture time of day changes, the atmosphere and the surface over 80% of the planet. And then it's going to catch the seasonal timescale. So it's a big picture look. It's not going to see the very close rock detail, look for signs of life that Perseverance and Curiosity are doing.
Well, thanks. That's, I mean, it's exciting to see how many different nations are actually endeavoring into this exploration. The Indian Space Agency has a mission orbiting Mars right now. The Russians are planning one, the Europeans are planning one, and of course we have these going. So it's just an amazing time to be exploring the solar system. The technology is there, and the political will is there, and we have the capabilities with all the engineers and scientists to really make this happen. So I think we're going to actually cut away here shortly. I just want to remind folks that there should be a briefing happening in about, I missed the sign that was just up there, but within the next hour or so, there's a post-landing briefing on NASA TV, and there should be updates coming throughout the hours today and tomorrow. So please keep checking in on the mission and enjoy the exploration of Mars. Thanks for being with us. Thanks to all of our panelists. It was a
definitely. And I just put in the chat a link to NASA TV if you want to keep following everything as it develops. And also next week on Thursday, we have a program for classrooms and school kids called Scientists in Action, where you can connect with another group of spacecraft engineers and Mars scientists. You can find that on dmns.org. Thank you for joining us. Especially thank you to all of our space scientists. This was so amazing, and what a great day. What a great, wonderful landing. And yeah, can't wait to see more pictures from Mars.
They'll be coming. Thanks again, everybody. We'll see you soon.